Hi, everybody. This is episode 22 of our podcast, Artificial Intelligence and Cybersurgery. Um, I am the editor-in-chief of a journal called Artificial Intelligence Surgery, which is the first journal that focuses exclusively on artificial intelligence and surgery. I'm here with my co-host, Dr. Vincent Grasso, who will introduce our next guest.
Sure. Thanks, Andrew. Hi, Vincent Grasso. I'm Director of Strategy and Social Media for the journal. And as Andrew said, we're the only surgical journal dedicated to all things AI. I have the great pleasure and privilege of introducing our guest. Well, what episode is this on, Andrew? 22?
22.
Amazing. Yeah, this has been fun.
Yeah.
Marios Pattichis, he's an interesting guy. He's a non-clinician. You've seen a lot of the clinicians on our show, but Marios is an interesting, very well-respected PhD, computer engineering, electrical engineering wizard. He's at the Department of Electrical and Computer Engineering at the University of New Mexico. I had the great privilege and pleasure of meeting his brother, who invited me in the Department of Computer Science in the University in Cyprus to come about 6 months ago in October to talk about healthcare and AI. And that's how I met Marios. So there was a connection through Cyprus researchers. What a great university that is, and an amazing island. Marios, we're happy to have you on our show. Can you just introduce yourself a little better briefly, and then we want to hear what you're doing with in AI and healthcare and radiology data sets and vision. So excited to talk to you. Welcome.
Hi everyone. Hi, thank you. Very nice to be here. Glad, very happy to talk with you. So I'm Marios Pattichis. I have a background, very diverse background. Studied computer science, mathematics, and then I did my master in electrical engineering and computer engineering. Here I'm a full professor of electrical and computer engineering, and my area of research, I work a lot with biomedical image processing and communications, even though my background is in the general area of image and video processing and communications. I'm the director of the online programs here at UNM. So happy to be here.
Nice.
Thanks.
Nice.
Go ahead, Andrew. Sorry.
No, I was just reminiscing how my wife was in Cyprus a few weeks back, and she was stunned at where she was staying at this beautiful hotel. And Vincent, I think you were staying there too, because you were giving
in
talks.
Limassol.
What conference were you at again in Cyprus?
Well, they hosted, basically they created a conference around our keynotes on healthcare and AI. So it was a conversational computing, machine learning, RPA discussion, and it took place in Nicosia at the university. And but I stayed in Limassol at a fantastic resort that your wife stayed at as well.
Is that what it's called? Limassol?
The Amara Hotel. Yeah, the Amara Hotel was
Hotel,
nice.
Yeah. It's I look forward to visiting Cyprus. I've been to Greece. That's about as close to Cyprus, and I've been to Lebanon also. So next time I'm gonna have to make it to Cyprus. Sounds like a beautiful island.
Yeah, super.
When did you move to the United States, Marios?
So yeah, I came in. I had what's called a full scholarship to study at the University of Texas at Austin in, now you asked me, 87. So yeah, that funded my bachelor's in computer science and another bachelor's in mathematics and a minor in electrical engineering, and that was by the U.S. government. I stayed there and continued. I guess by my PhD with Al Bovic, he created the first conference on image processing. I'm trying to remember when, I want to say 93, 94. And I was a student back then, and it was the time where image processing was taking over. It's taking off, and I never dreamed it would be so universal that it is right now. It was very expensive to do it back then.
So that's interesting. Can you explain, maybe for our viewers who are not computer scientists, what image processing is?
So the general area of image processing, video processing, and communication, so basically is involved with taking raw pictures, no matter what the source is, and processing them. And you study, I want to usually, for the purpose of what we're doing, we want to break it into two directions. One is you compress it and try to get video around, which is something we want to talk about in biomed. And the one that is the one catching a lot of attention nowadays is the idea of image and video analysis, where you analyze the content to do something very clever, like classify a radiograph or identify structures that might cause concern. So I usually, so the general image processing covers the whole, what kind of computer algorithms do you need to get this done? How do humans, a little bit less on the interaction with the humans, but mostly about processing the pixels that come through.
So I mean, is this digitizing images? Are those terms interchangeable?
So when you say digital image processing, it has been digitized already.
Okay.
So usually, so just to make the connection to Vincent, so like my brother, who is more traditional biomed, will be far more involved than I would be in the collection phase, even though I do teach the medical image analysis here in radiology, the medical imaging, sorry, in radiology. So I used to teach, sorry. So usually people call me when they've got big data sets. So, but now I'm involved in the process, in the collection as well.
Okay.
Yeah.
And what does your brother do? He's in healthcare, you just said?
His background is biomedical. So he has a biomedical lab versus mine, which is an image and video processing and communications lab. So typically, so our collaborations with Costas Pattichis back in that you guys saw is in so they will be in the front end of collecting from the doctors the data sets, even though I've done that too. But most of the time, my expertise comes in. Now you've got it. Well, how do you do it? What do you do? How do you process it? How do you compress it? How do you guarantee that it will be acceptable? How do you develop the system for analyzing it? I'm focused on that and much more.
Oh, interesting. So this makes a lot of sense about what we were talking about before he got on, Vincent. He would obviously be beyond ideal for what we were discussing, but we'll discuss that offline.
Yeah, we'll talk offline. But Marios has some slides to show us too of some of his work.
And I want to point out we actually recorded an episode earlier, but Marios was too kind and he gave us some data that hadn't even been published yet. So we're actually re-recording this without that data being presented. So we're going to have a follow-up podcast once the data is published. So yeah, please go ahead, Marios.
Thank you. So let me just start with the presentation. So I want to start the talk by this talking about the idea of universal video access for medical informatics. So one of the biggest things that is happening right now is that with the recent technologies, video compression and the new networks, we could actually communicate video anywhere, anytime, more or less, right? So in this example, which summarizes some of our work, we try to communicate an atherosclerosis, a plug ultrasound exam of the carotid artery as soon as possible. So you can see here, even from a moving ambulance, the idea is that you communicate the ultrasound video and you compress it and then you put it through the network and then you deliver it to the physician. The idea is anywhere, anytime. And the whole process here aims at fast response. That is, we would like to have, by the time the patient arrives at the clinic, we want to know if they need to be operated upon because we have seen the plaque that is unstable and might cause stroke, right? So, don't know. I can continue the next slide.
No, it's my brain was just thinking because I haven't done vascular surgery in quite a few decades, but I remember they were making decisions based on whether people would get carotid endarterectomies only on the degree of stenosis. They were basically using one, from what I can remember. I mean, they would have a few other factors if they thought that the thrombus was more likely to move or to embolize or not. But basically, it was stenosis. And I think of the amount of data that you're now looking at compared to what they're looking at. I mean, it's night and day. It's not even night and day. It's even more extreme than that. You're looking at so much more data.
So, so our work on predicting whether there will be a need or whether a plaque shall become symptomatic break. I'll break it into two parts. One, and this is work with Professor Nikolaidis from Imperial College, the doctor, and also my brother and his team in Cyprus. So we're looking at morphology. So basically analyzing with mathematical models what's inside the plaque. And then the second part, and that part, basically there are many hospitals leading hospitals throughout the world that use that software. And then the second part that I'll show you some example today that we're currently developing is looking at the mechanical properties of the plaque, if it's going to break or not, right? And that's an example of what I call video analysis, of analyzing the motions of the pixels. So just to continue here on the idea that we'll have universal video access, if you can deliver all medical records anywhere, anytime, then we can talk about the first application that we just looked at, which is the remote diagnosis and care for different modalities. And then, of course, we can have a remote diagnosis using teleoperated robotics. This is where Dr. Banagidis is working in Cyprus, and he's somebody that I share with my brother. So over here on this side, I worked a lot on the video compression to enable reliable communications. And then, of course, we have disaster emergencies, providing a second opinion, the doctor. And one that we are currently looking at right now is large-scale and interactive medical image analysis. And then, of course, I have search by content in computer-aided diagnostic systems and integration.
So that's interesting. Vincent, second opinion provision, I mean, I'm assuming that's similar a little bit to what Proximie does, which is basically just enabling doctors to communicate with other doctors quickly over the internet or over the network.
Well, yeah, Proximie doesn't do any image analysis. They just set up the video conferencing session between the two. So this would be, that plus image analysis. So that's an evolution of what Proximie does.
Right.
Okay.
That's great, Mario.
Yeah, so we'll show you.
Impressive.
So I'll show you some of the examples right here. This is a paper that we published in Nature Biomedical Engineering early on. We work with about 1 million cardiac ultrasound videos. So in these left examples, these are 3 examples of what we're working on. And in this example here, we have what we call a deep learning system, a convolutional neural net that is shown over here in this slide that we developed. I think it had about 100,000 parameters, which is a lot smaller than the large-scale systems that they use today. And even though it was trained on a very large data set, and it has 0 biases, right? Unlike the traditional systems you see now that have been processed on visual images, this one was essentially was developed for 17 different echocardiography views, and they were analyzed and they were put together, and the system tried to predict what we call the 1-year mortality, right? So basically, whether somebody will survive within a year, and that was easy to collect, the ground truth for it, right? So because we just pull out the medical records within a year and see if somebody survived or not. And you can see this line over here will be random guessing if the system didn't produce anything good. And then the little dots that you see everywhere, those are the red dots are the original cardiologists without any support. And then the blue line, the higher being the better, with the optimal point being up here, being the computer predicted model. And you can see that after training on 1 million, right, on echocardiogram views, the system was performing better than the cardiologist, right? So we wanted to do something to support the human in the loop. So in this example, we went back to the cardiologists on the cases that we had disagreement, where the system had predicted, let's say, that there would be the patient would die within a year, versus the cardiologist saying, no, they will be fine, and vice versa. So that essentially what you see here in this computer-assisted approach is that we asked, basically, we try to do a system with the cardiologist in the loop. And in that case, when we communicated with the cardiologist, we were asking them to look at it again. And when the doctors had the second opinion by the computer, we saw that they moved to the little blue dots. All of them improved, essentially. And we see them approaching what the machine can do. In other words, the joint cardiologists plus the system perform at least as good as the system, about the same as the system, within the margin of error. And this is very encouraging, because it shows you that by doing a model-assisted system, AI can really help reach a better decision. And I'll stop right here for this study if you have any questions.
I do. You mentioned 100,000 parameters. Now,
Yes.
Who comes up with these parameters?
So these parameters are built in what we call convolutional neural nets over here, right? In these boxes that we see here.
Yeah.
And it's, even though it sounds a lot, for the traditional deep learning that everybody's fascinated with, 100,000 is a lot less.
But
So essentially,
no, my
tell me.
point is another, and again, remember, you're talking, our
Yes.
audience, most of them are doctors. You're not coming up with the parameters.
No,
The computer is coming up with the parameters.
Right. So let me talk to you. Let me explain better. So basically, based on the, so over here, okay, it's kind of, I'm sorry, I'm going to use the magic. It's not magic to me, but just in some ways it is. So basically, based on the training, right, on the training data set, you know that a system. So basically, these parameters are initialized randomly, quote unquote, to process the image, the video, right? And what is happening is that originally, before the system learns the values for these parameters, it makes a prediction about the 1-year mortality, which is not going to be correct, right? So based on the difference right here on the output between what the system predicts and what the ground truth is, then we go back and change the parameters so that the error gets reduced. That is called training, right? So essentially, all those parameters were trained based on the ground truth, and then you iterate until the two come together where the system is able to predict correctly. Does it make sense?
It does. It does. I mean, this is a little bit. I mean, this is a little bit the concept of the black box.
Yes.
Right? No. I just like to review it for people so they can understand why artificial intelligence seems like magic, if you will. But the reason I wanted to bring it up is the ethical question. It's hard for us as doctors to explain to patients why we make decisions when they ask us, like, well, how did the machine make this decision, or what are the parameters? It's very difficult. It will be difficult for us to articulate these things.
That's why I have the second example on my right-hand side. But over here, so let me talk a little bit here. So yes, and these were the questions that we received when we published this study, right? So essentially, you can trace how the system processes the videos. You can look at the videos, but essentially, in this system and in modern AI deep learning systems, there are questions about what is happening, right? I mean, it's not so clear. Over here, back on the plaques, we have a much easier, and this is the one that is being used. This is the evolution of the system that is right now being used by the hospitals. So over here, we have an example where the system does not try to make a decision, right? The system is simply assisting the doctors to reach their decision based on visualizing the structure. So let me talk about it quickly. So here's an example where the doctor does explain, the system does explain itself. So over here, we have an atherosclerotic carotid plaque, which is in danger of breaking. And over here on the very, very top, I have the arrows and you can see there is a widespread of the different plaque components that make it very, very difficult, right? Very, very dangerous. I'm sorry. There is a possibility of breakage because all those different pixels move in very different directions. And we also have the plaque morphology over here, which shows you how the different components move. And you can see that this is a symptomatic plaque because the motions are everywhere, versus the asymptomatic class where the movement moves structurally in the same direction. Let me stop right here if you have any questions on this one. So this one we're trying to determine whether, so obviously the first one needs to be removed through surgery. The bottom one can stay because it appears far more stable.
I guess my question is why is the first image, why does the second image have more colors in it? What do those colors represent?
So yeah, so we have we use different colors based on whether it has more stable components. We looked at basically the grayscale, and we classified as, so there's a lot more calcified regions which are more stable inside the bottom plaque. That's my understanding.
Okay, I understand now.
Oh,
I understand. Oh, yeah. Okay.
And it's also moving in the same direction. So there are two things that has more stable components, and the one that we are working on right now is the motions. You can see that they move together. Therefore, if they were less stable, like here, which are much darker in the ultrasound, they move in many different directions.
Got it. Okay.
And another one we're working on here is the multiple sclerosis, which is essentially we can separate out. You see the green here is a patient after several years. So we analyze the content of the different multiple sclerosis lesions, and you can see that in the green case, the patient is fine after 3 to 5 years, versus the red, it progressed very quickly. And you can see in these plots, this plot shows you more like a texture content of the patient, and essentially the one with far more, in this example, diversity here, ended up has been associated with more multiple sclerosis events. Okay. And then I guess this is my last slide. Oops, sorry.
But sorry, on that last slide for 1 second, Marios.
Yes.
I'm having a hard time understanding what this image on the bottom, is it, where's this image generated from? It's
So
also
this is
ultrasound?
No, this is MRI. This is multiple sclerosis, a different problem. Sorry.
No, that's why, but I'm trying to understand. It's an MRI of the image that you're representing is very difficult. Is this a small region of the brain? What is it?
Correct. So what we isolated, we segmented out the lesions associated with multiple sclerosis in these two cases. So those are two different lesions. One associated with a patient.
Okay, it's not representing the entire brain. It's just representing a plaque. It's one region of where a plaque would be.
A lesion, yeah, a lesions in the brain, we call them.
Okay.
Multiple sclerosis lesions. Okay. All right. And then just a little kind of shows you what we're currently working on, and without sharing the details. So we're looking at the idea of large-scale video data sets. Where we analyze the videos, and not just videos, but also multimodal systems to support the clinical decision support. So we saw an example in echocardiology, but we're hoping to have much more examples in the future. In fact, we're right now working on a multimodal system. Thanks.
It's really exciting, Marios. That's fantastic.
I can continue.
It's amazing, and it's a shame our viewers can't see what you showed us the last time. But we're looking forward to sharing that with them. In how much time do you think you'll need to get that published?
So hopefully we will submit it in a couple of weeks, and then we will also publish it at the same time in archive. Yeah, we're looking at a very, very large multimodal system for the mortality risk assessment.
Say no more.
I'm sorry, what?
Yeah.
Say no more. It's
Say
all
no
right.
more.
Say no
Okay,
more. We
okay,
don't want to
okay.
say it's okay. The
All right.
temptation is too great. It's okay. We'll talk about it next time. Don't worry.
Yes, yes. I'm okay with
Well,
all that.
good news, Andrew. I'm going to be in New Mexico in about 2 weeks visiting Mario's at his laboratory and
Oh,
spending
fantastic.
2 days down there in Albuquerque and going over a bunch of different things that we'll be able to share with the audience. But this is going to be an exciting, I think, relationship with all of us. The cool, the interesting things we're all doing and working together, and should be a lot of fun.
No, I love New Mexico. Last time I was in New Mexico, I was a medical student, and I was doing family medicine in Crown Point Indian Reservation.
Yes.
So that was a surreal experience. We were about a mile up, and I remember, I went jogging. That was my one form of exercise. And when I got back to New Haven, I went jogging, and I literally went running for 3 hours. I normally went for 40 minutes, but I was like a Superman. It's amazing. You can really, those Kenyan marathon runners, they really have an advantage when they
Sure.
run at normal altitude.
Mario, so when you talk about having 1 million carotid ultrasounds, duplex Dopplers, when you have a data set that large, it's pretty massive. And if you're
Yes,
going to
we're
do
talking
machine
about
learning
echo,
on that, it's
echocardiography videos here. The million.
so they're big files, and 1 million of them is a massive
Yes.
amount of data. That's a big bill that you get presented by the cloud folks. Are you finding these to be very, very expensive? Certainly the prices come down to do all the computational work, or do you do them locally at New Mexico on your supercomputer there, or are you outsourcing that?
Oh yeah, sorry. This is with Geisinger, right? Geisinger collaboration. So let's go back a little bit here. So there are two things happening. First of all, for processing the data set, we use DGX2s, which is essentially a small supercomputer, right?
Yeah.
And it has massive amounts of storage, as well as GPUs, modern GPUs, several GPUs running in parallel to process the system.
Sure.
And but before you get there, of course, you got a lot of issues. You have to collect the data. What made this possible is, other studies where we basically were able to compress the videos so that they could actually feed in a single system, right?
Yeah.
So we did not process them in a distributed way. A lot of people are trying to do that nowadays. No, we put them in a supercomputer, and we just run it there. And this is compressed. So basically, especially for the large data set, including the one we're working on, right? Actually, we were cutting it into small chunks, but right now, for example, for our future, we need to compress things in order for them to feed. Okay.
Sure.
So Mario, for these ultrasound images, are you using a single image, or are you analyzing the entire video?
We're multiple video views. So we're literally looking at different views of the heart, like especially the 4 chambers.
No, well, I meant
17
for
videos.
the carotid plaques.
For the plaques, it's one video. The plaques right now, okay. So the plaques original studies that were done earlier, we was a single image, but in order to produce motions like this, you have to have video, because what happens is that the system goes through between the pictures and computes how the pixels are moving, right? And that's how we generate these motion vectors, right? That show you.
How long is the video?
They don't have to be very long, because it's based on the on the periodicity, right? So it could be only 100 video frames, but for 120 is what we use over here on the heart. But remember that because it's periodic and there is a lot of, so we only use, let me say a few more things. We only need 2 pictures to compute motion vectors, but they have to be further apart, right? So essentially, you want to present these movements are different parts of the cardiac cycle. So you need about, let's say you want to know what's happening in systole, diastole, and in between. So think in terms of cardiac cycles.
Nice. That's exciting. This is really exciting work. We can't wait to hear when you can talk about your other findings in a couple
Yes.
weeks. Okay.
Yes.
So that actually that's great, guys. We really we went through a lot, and we have a lot to talk about for our next episode with you. It's
Brendan,
really
just in closing, you and I are working on a paper for our audience to help them better understand, this whole space of video and compression and the stuff we're talking about. So hopefully we get to work with Marios in that too, and we'll be able to offer the audience something in a couple of weeks, right? That we're working on.
Yes.
Absolutely. Actually, I think what we're going to do, if it's okay, Marios, can you stay on for a few minutes? I just want to,
Yes.
Vince and I, we're going to talk to you a little bit longer, but we're going to take it offline, okay?
Okay.
About
Stop
another.
sharing your screen, Marios.
Okay. Thank you. I'll stop.
Yeah, great. We're back.
Thank you. I'm sorry.